Next we have the complexes of the type M, AB, ABCD. So in this, AB is also a didentate ligand, but both of the donor atoms are different. So this is the first possible pair. In this, again still the same thing, you cannot put AB in the same trans pair, you have to put them in a different trans pair, so they are cis to each other. So A is trans to A, B is trans to B, C is trans to D. Now this is also optically active. Okay, so there are no trans pairs getting repeated and no same ligands present trans to each other. So this is optically active. So this is the first possible pair. Next possible pair is A is trans to C, B is trans to B, small a is trans to D. So in this complex also this is optically active, again for the same reasons as the previous one was. This is also optically active. Now we have the next possible pair. In this, A is trans to D, B is trans to B, and A is trans to C. Again optically active. So 3 isomers till now, or 3 possible pairs till now, and all of them are optically active. Next we have A trans to small a, B trans to D, small b trans to D. Again this is also optically active. So 4 possible pairs, all of them optically active. Next we have A trans to A, B trans to B, small b trans to C. Again this is also optically active. So we had 5 geometrical isomers till now, or 5 possible pairs till now, and all of those were optically active. Now we go to the next possible pair. So that's A is trans to D, B is trans to C, and A is trans to B. Again optically active. So this was the 6th geometrical or 6th possible pair which was optically active. 7th possible pairs, let's see if it's optically active or not. So yes, this is optically active. You can look at the trans pairs and you can see B is trans to, this will be B, and C is trans to D. So this is also optically active. So that was, I guess, the 7th one. So this is the 8th one. A is trans to B, B is trans to C, A is trans to D. So this is also optically active. Now A is trans to B, B is trans to D, A is trans to C. Optically active again. Now A is trans to C, B is trans to A, and B is trans to D. So this is also optically active. Again A is trans to D, B is trans to A, B is trans to C. Optically active. Next we have A is trans to C, B is trans to D, A is trans to B. Again this is also optically active. So till now all of the possible pairs were optically active. So these were all the possible pairs for your complex M, AB, then AB, CD. So the total number of possible pairs were 12. So the total number of geometrical isomers is going to be 12. Now the total number of optical isomers, all of the geometrical isomers or all of the possible pairs are optically active. Now one possible pair which is optically active gives 2 optical isomers. So 12 optically active pairs will give you 24 optical isomers. Enantiomeric pairs is the number of optical isomers divided by 2. So that's again 12. And the number of stereoisomers is equal to the number of optical isomers plus the number of optically inactive pairs. So that was 0. So the total is 24. So you can see the total number of stereoisomers, geometrical isomers, optical isomers and enantiomeric pairs were same for the complex MAB, ABCD and MAA, ABCD. So next we move on to other complexes.